Hello all, I am Shatabdi Acharya from Vedang Institute of Technology. In today's video, we will take up a topic acids-base theory. So this is the third chapter of your module. So basically, somewhere or the other, the knowledge of acid and bases or the knowledge of entire chemistry, understanding the entire chemistry lies on the shoulder of acids and bases. So all the organic, inorganic reactions we come across in our chemistry modules, so somewhere or the other holds up or deals with acids and bases. So this chapter somehow plays a very crucial role in the knowledge of chemistry. So before proceeding forward, let's have a quick introduction. There are many practical methods to identify a substance as an acid or a base. Okay. So first of all, in order to understand the reactivity of any substance, we need to know whether it is an acid or a base. A acid or a base shows a characteristic reaction. Okay, a general characteristic reactions are shown by typical class of acids and bases. And there are various methods by which we identify whether a substance is acid or base. First example is, or the very common example is pH meter. Okay, the pH indicator according to which a substance which has a pH below 7 it falls under the category of acids, and the one above 7 falls under the category of bases. One lying on 7 is neutral, right? Next indicator is litmus paper. So litmus paper indicates whether an acid or base by the change of color of the paper. In general, excuse me, if I take up an acid turns a blue litmus into red color and a base does the vice versa. Okay, a red to blue litmus, blue color litmus paper. Okay, and there are various chemical reactions, like for example, metals react with acids to liberate hydrogen gas. So if I am reacting any metal with a general class of compound or a general, so let me say if I am reacting a metal M with HCl. Now, if I get in the test tube, if I get the liberation of hydrogen gas along with some salts, some metallic salts, then this falls under the category of metals. And how, I will test this whether the gas is acidic, hydrogen or something else. If I take a burning matchstick on the mouth of the test tube, it burns with a pop sound. That's the characteristic of hydrogen gas. So if I'm testing positive for this, then this class of compound is an acid. And if I'm not getting this reaction, obviously it falls under the category, it might fall under the category of bases. So, chemical reactions also can be used as a method to distinguish acids and bases. However, theoretically it is now possible to know whether a substance is acid or base. Okay, every time if I am saying, suppose on pen and paper I am writing and saying whether H2SO4 is an acid or a base. In that case, you cannot run to the lab to test whether it is an acid or base, right? So there has to be some theory or some logic by which you can just simply by looking at the structure or phenomenon or the reactions of H2SO4, you can know whether it is an acid or a base. Okay, so accordingly, in order to classify substances into acids and bases, various theories have come up, but the very important ones are Arrhenius theory, Lowry-Bronsted theory and Lewis theory. Okay, these are three important theories which relate to the definition or classification of compounds under the category of acids as well as bases. Now let's see what did they say about this acids or bases. Okay. First we'll take up Arrhenius theory. According to Arrhenius theory, acids are those substances which give H plus ions, okay, which furnish H plus ions when they are dissolved in their aqueous solution. Let's say if I am adding HCl drop by drop to water. Okay, here let me address a very important thing. Whenever we are adding or mixing, we are trying to mix acid as well and water together, then always the acid is added to the water drop wise from the brim of the test tube, because the reaction of acid and water is highly explosive. Okay, so always acid is added drop wise to water and never water to acid. Okay, so according to Arrhenius theory, acids are the substances those which furnish H plus ions or protons in aqueous solution. So when I am dissolving HCl in water, if there is liberation of H plus, if in the medium I find any possibility of H plus donation, then they fall under the category of acids, and bases are those substances which produce OH minus in their aqueous solution. Let's say I am taking NaOH. So simply by looking at the structure only, you can say it has the possibility to liberate OH minus in solution. Therefore, I can classify or safely classify NaOH into the category of bases, and HCl, as it poses the possibility of liberation of H plus ions, I can classify it under the category of acids, right? So example of acid, HCl, when it is mixed with water, it breaks off into ions H plus and Cl minus. Other examples are HNO3, H2SO4 and acetic acid or vinegar, which is CH3COOH, although it is a very weak acid. Next is example of bases. If I say, then NaOH, when dissolved in water, it breaks off into Na plus and OH minus. Other examples being LiOH, KOH, NH4OH, CaOH whole 2, AlOH whole 3, etc. So in the structure, wherever I find the possibility of donation of OH minus, they are classified under the category of bases, and the structures where there are possibility of H plus donation, they fall under the category of acids. Now, if I take the salient features of Arrhenius theory, okay, so theory was simply proposed, okay, a statement was given by Arrhenius that acids release H plus in aqueous solution, base gives off or releases OH minus in aqueous solution. Now let us see what are the features of this reaction. So the first one is, according to Arrhenius theory, an acid reacts with a base to form salt and water, and that reaction is called as neutralization, which you have been studying since your school, right? So whenever I am taking HCl and reacting it with NaOH, HCl being an acid reacts with NaOH, which is a base, and a typical acid-base reaction produces a salt which is known as common salt, NaCl, and water. Okay, this is a typical acid-base reaction. Neutralization reaction may be represented as the H plus comes from the acid, the OH minus comes from the base, they react together to form water. Okay. Higher is the degree of dissociation, higher is the acidic or basic nature of the substance. Now, this statement is somewhat crucial in classifying acids or bases into weaker and stronger categories. Now, in the previous slide, I have given you example of, one second, yeah. So here I have given you example of HNO3. Let me just compare HNO3 and CH3COOH. If I see HNO3, it dissociates into H plus plus NO3 negative, right? Now if I say vinegar, it breaks off into CH3COO minus plus H plus. So see, in the first case, what I see is, in case of HNO3, all the whatever possible hydrogen atoms or protons which were present got dissociated into H plus and the respective negative counter ion, right? But in case of CH3COH, I still find 3H which are undissociable. These H cannot be by any chance dissociated. Hence, if all the bonds or all the H plus protons are dissociated, then it falls under the category of strong acids, and if partial decomposition or partial dissociation occurs, they fall under the category of bases. Sorry, weak acids. So if I see H2SO4 similarly, H2SO4 has the ability to give 2H plus 2H plus SO4 2 negative. So here also H2SO4 has a tendency to dissociate all the possible protons, and hence it falls under the category of strong acids. So strong that is called the king of chemicals, okay, the king of acids. But okay, every theory has, there are two sides of a coin, like, right? So like that, every theory has some pros and cons. There are certain limitations of this theory. So let's look what are this. The first thing is H plus ion does not exist in aqueous solution. Okay, H plus being a proton, it is not stable. As soon as it is formed, it combines with water to give you hydronium ion. Okay, whenever H plus is released, it combines with water. The lone pair in water accepts that H plus to give you H3O plus. Okay, the structure of H3O plus with a positive charge on oxygen. Why? Because the oxygen has reacted through its lone pair only. Okay. This theory fails to explain the acidic and basic nature of substances in solvent other than water. Okay. So, this theory fails to explain why a substance behaves as an acid or a base in solvents other than water. This theory fails to explain the acidic nature of substances like SO2, CO2, SiO2, P2O5, BF3. BF3 has got a certain like a particular name called Lewis acid, but it has acidic character. But simply by understanding Arrhenius theory, we couldn't explain the acidic nature of these compounds. Okay, SO2, CO2, SiO2, phosphorus pentoxide, BF3, AlCl3, which cannot provide H plus ions. Okay, these do not have any potent H plus in their structure. Though, so as per, if you are only considering Arrhenius theory, as per this theory, these all do not fall under the category of acids or bases, but they have acidic nature, which later theories came forward and were capable of like making us understand the acidic nature of these substances. Okay. Now, if I see the other limitation, this theory fails to explain the basic nature of substances like NH3, PH3, Na2O, K2O, CaO, which do not have similarly OH minus ions. This theory fails to explain the neutralization reaction between some acidic and basic substances that do not produce water. If I see this HCl and NH3, what happens? This H plus and Cl minus, they combine with this NH3 to give you NH4Cl. So this is also an acid-base reaction. NH3 is a base, HCl is an acid. They give you a salt NH4Cl, but there is no liberation of water. So as per this theory, this cannot explain the neutralization reaction between these substances. Okay. So considering these limitations, a new theory crept in, which we call the Bronsted-Lowry theory. So let's see what it is. According to Bronsted-Lowry theory, acids are the substances which donate proton, okay, which donate H plus ions, and bases are the substances which take up proton from any other substances. Those have the tendency to take up H plus. Okay, so if I see this reaction, here HCl was having a tendency to give one H plus to ammonia, and as ammonia is having a lone pair, through that lone pair ammonia has a tendency to take up this H plus to give you ammonium salt, NH4 plus. Okay. In other words, acids are proton donors, whereas bases are proton acceptors. For example, here, the example I was giving you just now, HCl takes up the H plus from, ammonia takes up the H plus from HCl to give you ammonium ion plus Cl minus, okay, chloride ion. Since HCl has donated a proton to NH3, it acts as an acid. On the other hand, NH3 has accepted a proton from HCl and thus it acts as a base. Got it? Now, if I see other examples, all Arrhenius acids are Bronsted-Lowry acids, because according to Arrhenius, acids are H plus donors, and Bronsted also was agreeing with the fact. Okay, acids are H plus donors. However, the reverse is not true. Okay, all Arrhenius acids are Bronsted-Lowry acids. However, the reverse is not true. That means all Bronsted-Lowry acids are not Arrhenius acids. Ions having the capacity to donate H plus ions also fall under the category of acids, okay, according to Bronsted-Lowry. So if I see this ions, HS minus, HCO3 minus, HPO4 minus or HSO4 minus, they also have a tendency to give H plus ions. So here the concept of conjugate acid base pairs comes into existence. Okay. Example, if I see, I will explain the conjugate acid base pairs in a while. Let me give you the example of bases. So natural molecules like OH, H2O, NH3R and H2, whichever is having a lone pair in its structure, fall under the category of bases. Similarly, the other ions which have a capacity to take up the H plus also fall under the category of arrhenius base, Bronsted-Lowry bases, just like OH minus, Cn minus, HCO3 minus. Okay. They also being negative, they also have a tendency to take up the H plus ions to form a base. Okay. So salient feature is, according to this theory, an acid reacts with a base to form another pair of acid and bases. Now this another pair of acid and bases is what I call conjugate acid and base. So let me explain you with an example. See, if I say H plus, HCl, sorry. Now this HCl has a tendency to give H plus. Okay, so it breaks off into H plus and Cl negative. So as it is able to give this H plus, this falls under the category of acids. Now what happens when this Cl minus is remaining free in the solution? Now the Cl minus is also having a tendency to take up the HCl or any H plus from the vicinity. Okay. So if I see only HCl, then HCl breaks off as H plus plus Cl minus. Now this H plus is the acidic proton which left the HCl structure. So this was an acid. Now when the acid breaks off, when the acid gives off the H plus, it forms another substance or another ion, I may say, now which has the counter tendency. That means it has the tendency to accept electron now. So these pair of acids, and this will act as a base. So these pair I call as conjugate acid base pair. So if an acid is liberating H plus ion, it results in the formation of its conjugate base, which now has a tendency to take up H plus. Okay. So this is what I call the conjugate acid base pair. Now if I move on to this example, here HCl gave off its H plus, it liberated the Cl negative, which is the conjugate base. Okay, if this is the acid, then this is the conjugate base. Now in case of ammonia, if I see, the ammonia took away the H plus which was liberated by HCl, it formed NH4 plus. Now this ion also has a tendency to liberate the H plus whichever it has taken. So if this is the base, then this forms its conjugate acid. So this is a conjugate acid base pair. I hope you understood what the concept of conjugate acid and conjugate base is. An acid always results in the formation of its conjugate base, and a base always results in the tendency or the formation of its conjugate acid. Okay. Now the substances which such as water, HS minus, HCO3 negative, HPO4 2 minus, HSO4 negative, which act as both acid donor as well as acceptor, are called as amphoteric substances. Okay, those substances having the tendency to give off H plus and take up also similarly. Okay, like depending upon the situation, they can act as an acid or a base. Those are called as amphoteric substances. Now, one of the very important point to note here is, suppose I am saying HCl, right? I say HCl is a strong acid. What does that mean? It means HCl can easily liberate its H plus. That's why it's a strong acid. Okay, so I can say HCl is a strong acid because it is giving off the H plus and Cl minus very easily. Now, suppose H plus is having a very strong affinity for Cl minus. Okay, suppose H plus has a very strong affinity for Cl minus. then will HCl be ever willing to lose its H plus? No. After breaking off also, if that like attraction would be there, then Cl minus would always want to take up the H plus. Then in that case, whether this acid or will this acid be able to behave as a strong acid? Obviously no. So, acid is considered to be a strong acid whose conjugate base is weak. Conjugate base is weak. So from this I can come to the conclusion that a strong acid has a weak conjugate base and vice versa. A weak acid, I consider an acid weak because it has a strong affinity for H plus. So if at all it is breaking off its H plus, it will always have the affinity to take that H plus back, right? So that's why that acid will behave as a weak acid, but because it will not give sufficient amount of stable H plus ions. So I can say a strong acid has a weak conjugate base and a weak acid has a strong conjugate base. Similarly, it is the case with bases also. Got it? Now, some of the limitations of this theory are, it fails to explain the acidic nature again, which was that of Arrhenius also. So, it fails to explain the acidity of SiO2, CO2, SO2, BF3, etc. It fails to explain the basic nature of, it was somehow capable of explaining the basic nature of NH3, right? NH3, H2O, it was able to explain. But still, Na2O, K2O and CaO are remaining under the dearth. Okay, it could not explain the basic nature of these substances which cannot accept H plus ions. Now again, it fails to explain the reaction between some acids and bases which do not give another pair of acid and bases. For example, if I say HCl, NaOH, they react with each other to give you NaCl and H2O. Okay, so here it is not giving another pair, it is a pair of salt and water. It is not giving a pair of acid and bases. As per Bronsted-Lowry, an acid and base react with each other to give you another pair of acids and bases. But in this case, it's not possible or it's not happening. So it was not able to explain this neutralization concept here. Okay. Now here I am giving you some acid and their conjugate bases and some bases as well as their conjugate acids. So first of all, if I take HCl, here HCl will be breaking off into H plus and Cl minus. This Cl minus is termed as its conjugate base. If I say H2SO4, then its conjugate base will be HSO4 negative or SO4 2 negative if it has lost 2 H plus. If I say HS negative, its conjugate base will be S2 negative. That of NH4 plus will be NH3 after the loss of H plus. Water will lose one H plus to give you OH negative. And if I come down to bases, Br minus will react with H plus to give you HBr. Now it is always having the tendency to lose the H plus. Cn minus will give you HCN. O2 negative will give you OH minus, NH3, NH4 plus, and water will take plus H plus to give you H3O plus, hydronium ion. Now, after the certain limitations of Bronsted-Lowry, another concept took its place, which is called as the Lewis theory. So now let us understand Lewis theory and see whether Lewis theory was able to explain or overcome the drawbacks of Bronsted-Lowry or not. So, according to Lewis theory, acids are substances which, okay, they can be molecules, neutral molecules or ions as well, okay. So, acids are substances which can accept a pair of electrons from any other substances, okay. Acids are here not H plus donors, acids are electron acceptors now. Acids are electron acceptors. And base will be the opposite ones, that they will be donor of electrons. So, bases are substances which can donate a pair of electrons to any other substances. So, here what they explained is acids are E negative or electron acceptors and bases are electron donors. Now, if I say acids are electron acceptors while bases are electron donors. Now, example of acids which is cations like CH3 plus H plus, etc., they have a tendency, being positive, they can take up electrons from any sources around their vicinity. Next is neutral molecules like electron deficient atoms are Lewis acids. For example, I was saying, let's say BF3. Okay, it is trigonal planar in structure. So if I say BF3, boron atom is forming bonds with 3 fluorine atoms. So boron has only 6 electrons around its vicinity. But as per octet's rule, an element must have at least 8 electrons to be considered stable. So it is lacking a pair of electrons. Similarly, AlCl3, FeCl3, ZnCl2 all are surrounded by electron or number of electrons less than 8. Therefore, they fall under the category of Lewis acids because they always have a tendency to take up the electrons from their sources around their vicinity. Then again, neutral molecules containing vacant d orbitals, okay, where they can accept or accommodate in another pair of electron, they fall under the category of acids also. Like the Lewis acids like SiF4, SiCl4, they all fall under the category of Lewis acids. Okay, basically D block elements, they have a tendency, not exactly D block, but the one having vacant d orbitals. Okay, they have the tendency to accommodate the extra pair of electrons, considering or which makes them fall under the category of Lewis acids. Next is the molecules having multiple bonding. Okay, multiple means pi bonds, and pi bonds are weaker bonds which can easily break. Therefore, they fall under the category of substances which can accept electrons between the atoms of different elements are acidic in nature. For example, CO2 if I see. Then there is a double bond between carbon and oxygen. So anyways, the double bond will break off as O negative and carbon plus. Now here the carbon plus has a tendency to take up electrons now because it is positive. Therefore, it acts as a Lewis acid. Similarly, SO2 also. Now if I say example of bases, again they are electron donors. So obviously the ones having negative charges or lone pairs on them, they will fall under the category of Lewis bases. Examples F minus, Cl minus, CO3 2 minus, etc. And neutral molecules of NH3, PH3 and H2O because they have lone pairs. What are the salient features of this theory? According to this theory, an acid reacts with a base to form a coordinate or a dative bond. For example, the reaction between NH3 and H. Now, NH3 has a lone pair of electrons. It somehow gives its lone pair to H plus. By this coordinate or dative bond, they form a pair of acid, or this reacts like H plus, it is giving it off its lone pair of to H plus to give you ammonium ion, and therefore it falls under the category of Lewis bases. It is electron donor. All Bronsted-Lowry bases are Lewis bases, while the reverse is not always true. Now what does that mean? According to Bronsted-Lowry theory, okay, what were bases? Bases were H plus acceptors. So here it is saying electron donors. According to Lewis theory, bases are electron donors. And according to Bronsted-Lowry theory, bases are H plus acceptors. So the one having lone pair of electrons or negative charge will be able to accept the H plus. Therefore, all Bronsted-Lowry bases are Lewis bases, but the reverse is not true. Now, if I see the limitations of this theory, according to this theory, the reaction between an acid and a base results in the formation of a dative bond. Formation of a coordinate bond is a slow process, while the reaction between acids and bases are instantaneous or fast. Acid-base reactions are fast, but dative bonds are slow. So they are counteracting each other. This theory fails to explain the relative strength of different acids and bases. Okay. It fails to explain the reaction between some acids and bases where no coordinate bond is formed. It fails to explain the acidic nature of well-known acids like HCl, HNO3, H2SO4 because they are not electron acceptors, okay, which cannot accept electrons. It fails to explain the basic nature of well-known acids like NaOH, KOH, which cannot donate electron pairs. It fails to explain acid-catalyzed reaction where H plus ion plays important role. So from this, all the three theories, what conclusion we can do draw is, and none of the theory is able to justify or to give justice to the exact definition of acid and bases. We can only consider a substance as acid or bases, or we can take up any acid or bases depending upon our desired reactions. Okay, any particular substance is, if one particular theory is able to explain the acidity of any particular substance, the other theory counteracts it. Got it? Now let us take up neutralization reaction. According to Arrhenius theory, acid react with bases to form salt and water. This process is called as neutralization. Now, here we will take up, we know whenever neutralization occurs, it results in the formation of salt plus water. Now, we also know an acid can be a strong acid and weak acid. A base can be a strong base or a weak base. So, depending upon the strength of the acid and base, the nature of the salt will also vary, right? So, let us see how that happens. If I say neutralization between a strong acid and a strong base, so the strong acid reacts with a strong base to form a normal salt, okay, or I can say a neutral salt. Both are equally strong, so the salt form will be a neutral one. The aqueous pH is about 7 and is neutral. Now, if I say strong acid and a weak base, in this case, what happens? The acid part dominates and the base part is like kind of submissive. So, the salt here will be an acidic salt. Got it? So, an acid reacts with a weak base to form an acidic salt. Its aqueous solution pH is less than 7 and the solution is acidic. Example is NH4Cl. Now, neutralization between a weak acid and a strong base. Here the acid part is kind of submissive and base dominates. So, the salt form will be a strong or a basic salt. Okay. pH is greater than 7 and is alkaline. Example is CH3COONA. Neutralization between a weak acid and a weak base. Now, here also both the counter ions are subtle. So, the salt form will be a neutral salt. The one between CH3COOH and NH4OH. Now, let us see a definition of salts. First definition is, salts are regarded as ionic compounds made up of positive and negative ions. The positive part comes from a base and the negative part might be coming from an acid. Okay. Now, second definition is, salts are ionic compounds which produce cation other than H plus and anion other than OH negative. Third is, salts are the compounds formed by neutralization between acids and bases. Now, if I see some types of salt, which is normal salt, acidic salt, basic salts. Okay, what are normal salts? Which are neutral. They are formed by strong acid and strong bases. Got it? So, you can see these examples also if you want. So, normal salts are obtained by complete replacement of all the replaceable hydrogen atoms of an acid by metal atom. It is called a normal salt. These salts are obtained by the reaction between strong acids and strong bases. Examples are given here. Here again, acidic salt means the salt formed between a strong acid and a weak base. Again, examples are here. Also, these salts are obtained by neutralization. Got it? Next is basic salt, the one formed by the reaction of weak acids and strong bases. Example, CH3CONA, CH3OK, Na2CO3, K2CO3. Now, the important thing to note here is a double salt. Double salt, these are molecular addition compound obtained from two simple salts. Here what happens, two simple salts, they combine with each other, which retain their identity in aqueous solution. Okay, when in aqueous solution, when they break off into their respective ions, they don't lose their identity, but they are retaining their identity in aqueous solution. Such salts give the test of all the constituent ions when dissolved in water. So, for example, if I am taking NH4Cl and let's say MgOHCl. When these substances break off, they will give test for NH4 plus, Cl negative, Mg2 plus, OH minus and Cl negative. Okay. These ions, they do not lose their identity. The identity of these particular substances are intact. If I see the next example is the K2SO4 dot Al2SO4 whole 3. not 24H2O, which is commonly known as the potash alum. When they break off in water, they give you K plus, Al3 plus and SO4 2 minus, and they give test for all these salts only. Okay. Excuse me. Next is complex salts. These are the molecular addition compound obtained by the combination of salts, the ions of which lose their identity in aqueous solution. Such salt do not give test for all the respective ions. For example, if I am saying K4FeCN6, so you might be expecting whenever it is neutralized or whenever it is added to water, it will release K plus, Fe2 plus or whatever the valency is 2 plus or 3 plus and Cn negative. But no, whenever it is ionized, this part, this is basically a coordinate salt, okay, coordination compound you will be studying. In that like particular part, these salt is falling into. So here what happens, it just breaks off into K plus and FeCN6 4 negative. Here what happens, the coordinate part, they do not lose their identity. Here the ions are intact. Okay, so this is a complex salt. In a mixed salt, what happens? These are the salt which give either more than one cation or more than one anion in aqueous solution. For example, if I say bleaching powder, CaOCl2. So when sodium potassium sulfate, NaKSO4, etc. So when these are like dissolved in water, what happens? This bleaching powder gives you ions Ca2 plus, OCl negative and Cl negative. Okay, 3 different type of ions. Similarly, Na sodium potassium sulfate, here what happened? It gives you ions like Na plus, K plus and SO4 2 negative. So they form under the category of mixed salts. Okay. So these were some of the chapter acid base theory. Here we have dealt with all the 3 theories of acids and bases, neutralization reaction and the types of salts. And the next lecture we will take up another module from a chapter. Till then, thank you so much.